Hello everyone. In this video we're going to talk about graphing sine functions. So the kinds of functions that we're considering are of a very specific form, and that is of the form a times sine of omega x minus phi. A is a quantity known as amplitude, omega is a quantity known as angular frequency, and phi is a quantity known as the phase. Usually phi is in the range of 0 to 2 pi, but there's no reason to limit yourself to that. So, first amplitude. Amplitude controls the maximum and minimum values that the function will have. So it goes up to positive a and it goes down to negative a. The next quantity, angular frequency, controls the period, and that's 2 pi over omega. That is the distance between the first crossing here, for it to go up and then down and then back up to the x-axis. So that distance between those 2 points is 2 pi over omega. And the position of one of these crossing points, the first one for this cycle here, is phi over omega. So knowing omega gives you the period, and then additionally knowing phi gives you the location of one of these zero crossings. It's the horizontal displacement of the sine function. That's what the phase controls. So, one question. Why is the formula phi over omega? And the idea is that since we're wanting to know where the zero crossing happens, we want to know when are we plugging 0 into the sine function, because that's what the sine function looks like when it crosses, when the input is 0 and near 0. So solving omega x minus phi equals 0, for x, we get phi over omega. Next question, why is the period 2 pi over omega? Well, the idea is that if we plug x plus 2 pi over omega into this function, so replacing x with x plus 2 pi over omega, that represents going forward by 2 pi over omega and seeing what happens. Well, if we distribute the omega, we get omega times x plus omega times 2 pi over omega. The omegas cancel out and we have 2 pi, and we have minus phi there. And then remember, one of the identities, one of the basic identities for the sine function is that if you add 2 pi to the argument, it's the same value as when you don't add 2 pi at all. And that is because, remember, an angle is the same as the angle when you add 2 pi to it, because it's adding in one full revolution. Okay, so we have some understanding of that. And as I was saying, the phase could be between 0 and 2 pi. That's one way that you might want to normalize it. So the reason for this is the same identity business. We can add or subtract multiples of 2 pi to phi without changing the graph at all. And by adding enough multiples of 2 pi, we can always bring it into this interval. And I should say, in this notation, remember, we're including 0 and excluding 2 pi. And why do we exclude 2 pi? Well, if it were 2 pi, we could subtract 2 pi and get 0. So may as well just use 0 instead. And then graphically, the idea is that by adding 2 pi, we're shifting the entire graph over by one full period, and that's the original graph. So there's no point in keeping around exactly how many multiples of 2 pi it is away from the actual phase. Okay, so for example, let's say we had y equals sine of x minus 9 pi over 4. In this case, a is 1, the angular frequency is 1, and phi is 9 pi over 4. Since if we subtract, okay, so yeah, 9 pi over 4, how big is that? It's a bit bigger than 2 pi. If we subtract 2 pi, we get pi over 4, and that's certainly in the range from 0 to 2 pi. And so that is the exact same graph as y equals sine of x minus pi over 4. Yeah, so pi over 4 may as well be the phase. One last thing I want to mention before we go and play around with the graphing calculator is that there's a pretty common way that these functions show up is with some sort of vertical displacement. So vertical displacement's a straightforward idea. If you add c, it shifts the entire graph up by c. And how does that look for this sine function? Well, first of all, because without the c, it goes up to a and down to minus a. Now we go from c plus a to c minus a. Those are our new bounds. And then c is this like center line. That's exactly halfway between them. This phi over omega is controlling when it crosses the center line, and then when it goes through a full phase, that would be when we're adding in 2 pi over omega to get the full period. Okay, so now what we're going to do is switch over to the graphing calculator and control some parameters. So in this case, rather than using omega, I am using little c, and rather than using phi, I'm using p. So let me reset these values for a moment, or give me a moment to reset these values rather. So I'm setting the phase to 0. Okay, so if I control the amplitude, so it's at 1 right now, so it goes from -1 to 1 for the range. There's the amplitude to 2, amplitude to 3, amplitude to 4. So increasing the amplitude just makes the function taller. There's also negative amplitudes, just watch out for that. But generally, it's, amplitudes being positive makes a bit more sense, so let's stick with that. So the phase, the angular frequency, if I increase the angular frequency, then the period goes down. Because remember, it's 2 pi over c is that is the period. So increasing the angular frequency makes the period smaller. So if I make it, for example, 3.1, which is close to 3.14, pi, then it, over the course of 2, it manages to do a full cycle. If I make it be 2 pi, which is about 6.2, then what happens is the period is 1, which we can see there. So let's reset that to 1 for our period. Now, p equals 0, that's our current phase. If I increase it to a full 6, or a full 6.2, which is about 2 pi, we're back to our original graph. So that's why adding and subtracting multiples of 2 pi does not change anything. I can also subtract 2 pi, and then that goes backwards by a full period. Okay, let's reset that. And also, if I increase this increased angular frequency, it's still the case that going through a full 2 pi is what brings it through a full period. And also, one last thing here. I said that positive amplitudes sort of make more sense, because making it negative means that the maximum is now, so it's the amplitude's -1, right? So it's going from -1 to 1 still. But now the whole thing's flipped over. But if I shift the whole thing over by pi, then we're back to the original graph. So in some ways, negative amplitudes are not necessary, because you can always shift the phase by pi to reproduce that sort of negative amplitude. So anyway, that was graphing sine functions. There's a lot more that can be said, but let's keep this video short. I'll see you next time. Bye.